Let's get started, everyone. Thank you, everyone, for joining. Good morning, good evening, good afternoon. Thanks for joining this tinyML talk. Today, we're going over the CFU Playground, customize your ML processor for your specific tinyML model. And today we have a special guest, Tim Callahan from Google. So thank you, Tim. The tinyML Talk strategic partners, we definitely want to do a shout out for all of them. And thank you. That's Aeon Devices, ARM, Deep Light, Edge Impulse, EMSA Visual Sense, Green Waves Technologies, Gravity Inc., HOTG, ImageMom, Kilka Tech, Latent AI, Analog Devices, Micro AI, NXP, Prophecy, Qualcomm, Kixo, Reality AI, Renaissance, Rixen, SAP, Seed, SenseML, ST, Stream Analyze, SynSense, and Syntiate. Additional sponsorships available. Please contact Olga at tinyml.org for info if you're interested. Okay, the tinyML Summit 2022 is coming in March 28th to the 30th. Enrollment opens in January, so make sure you keep checking the website. There'll be a big announcement when enrollment opens, and registration, so you can sign up and attend. It will be at Hyatt Regency in San Francisco Airport. There's also the tinyML Research Symposium this year again, and that will be March 28th, so the day right before the summit. More sponsorships are available at sponsorships@tinyml.org. Okay, join the growing tinyML communities either through Meetup or LinkedIn. There's the tinyML community on LinkedIn. Through Meetup, there's lots of local different meetups around the world that are hosting their own talks. Make sure to check those out. Join one that's local to you. At some point, we're doing more in-person things, but I think we've shifted back most of them to virtual. But check it out. There's everyone around the world, so you can find one in your own time zone. Subscribe to the tinyML YouTube channel for updates and notifications, including this video and all previous videos. That's at youtube.com/tinyml. The next tinyML talk will be Tuesday, January 18th, and that's Ashutosh Pandey from Infineon Technologies. And he will be going over exploring technologies to build efficient and robust tinyML deployments. Webcast start time is 8 a.m. Pacific time. Please contact talks@tinyml.org if you're interested in presenting. And with that, I'd like to introduce our presenter. Tim Callahan works at Google with the open source FPGA toolchain SymbiFlow team. His work is to help make FPGA development more accessible, fun, and rewarding. His research interests include anything that involves optimizing the hardware-software boundary. He has degrees from UC Berkeley, Cambridge University, and the University of Minnesota. With that, I will hand it over to Tim. And Tim, thank you so much for presenting today.
Well, thank you, Carl. Thank you, Olga and Evgeny, for inviting me. I'm really happy to be here. And as you said, I love questions, so let the questions flow. And if there's not time, send them afterwards. And I'm happy to chat with you. I'm Tim, I'm presenting, but this is the work of many. Disclaimer, this is not an official Google project. It is an open source project. So come check it out on GitHub. The other Googlers who work on it, primarily Alan Green, he's written the majority of the custom function units that I'll show later. David and Dan were instrumental in getting this project going. My manager, Tim Ansel, had the original idea and let me work on it, so thank you, Tim. And interns Rachel and Joey contributed a lot in their brief stays at Google. And of course, thank you to the TensorFlow Lite for Microcontrollers team, headed by Pete Warden. Ant Micro is a firm that did a lot of work with us directly on CFU Playground, and also they created Renode, which is one of the open source tools that we use. We have a relatively new collaboration with Professor Reddy's group at Harvard. We contacted them initially to get some of their ML-perf tiny benchmarks integrated into the CFU Playground, and we're expanding that collaboration to develop a workshop, so look for that in the next few months. And mainly, thank you to the open source community. All these tools that we're using rely on open source. So in detail, it's really a showcase of these open source tools, starting from the ML library, TensorFlow, the Open ISA RISC-V that lets us extend it, And not only is it open, but there's a number of good FPGA implementations. We're using Vex-RISC. Litex lets us build a board level system on FPGA boards very easily. We're using open source tools for building the FPGA bit stream. I'll explain that in a little bit. We use Python for generating the custom function units. That might get some of you a little curious, so I'll talk more about that later. Even the simulators that we use are open source. So pretty much everything is open source except for the FPGA itself. And even that might change. We're not working on that, but we know people who are working on making open source FPGAs. So the benefits, you might think, well, yeah, of course, it's free. But I mean, that's really not, for us anyway, it's not the main benefit. It's more the licensing headaches, trying to get licensing in our cloud build system, and even getting a third-party proprietary tool into our build system is a lot of headaches. Because it's open, we can fix things, we can extend things as we want. We're not locked into a vendor, which, you know, that might sound a little harsh, especially if you're a vendor, but it's mainly so that if there's like a supply chain issue, we have the option of switching to another FPGA at the last minute, and it'll still work pretty well. And mostly transparency. This is kind of a trust issue. Do you need to trust this, either the software or the hardware that you're using? There's this really interesting other project that is not related to CFU Playground, but they use a lot of the same open source that we do, called Be Trusted. And they are going to the extreme that they don't want to use a CPU. They want to build their own processor on an FPGA. So anyway, coming back to CFU Playground, the key ideas for tinyML is that you are going to specialize the entire stack just for your particular model. So you're not including both the ML library and the processor itself. We're not building an accelerator for all models, but you will specialize it just for the one model that you're interested in. And we also want to make it easy to get started and allow really quick iterations so that you can explore the design space. That just means you can try a lot of different things. And building a fixed instruction set, building a new instruction set, or even extension is really difficult because you have a lot of people that you're trying to keep happy. In this case, you're only building the extensions for yourself. And the other thing is, if you make a mistake, it's no big deal because you can change your mind tomorrow. You're not committing to silicon. Okay, how can we do this? How can we build our own hardware? So here's a one slide background in FPGAs. It is, FPGA stands for Field Programmable Gate Array, which basically means that you can program the hardware. It's software-defined hardware. You download a string of ones and zeros, just data, and it tells each of these blue blocks what small function they're supposed to compute. And it also sets the switches in the interconnect network to hook them to each other and to the IOs. And so by downloading one bit stream, you make it act as a certain circuit, and then you download a different bit stream and it'll be a different circuit. The FPGAs that we use range from 5,000 of these logic blocks up to 100,000. And they all contain also hard multipliers and embedded small memories, because those two structures are pretty inefficient to implement with this generic reconfigurable hardware. So you will be running your inference on an FPGA board like this. Instead of a microcontroller, we have an FPGA in the middle. And again, it's nothing until we do something with it. There's a USB port that we use like with an Arduino, you use it to communicate with your laptop and also to download the software that's running. And in our case, we also use it to download the bit stream that configures the FPGA. Okay, so what are we going to build on our FPGA? Well, we're going to start with the CPU, again, using the RISC-V instruction set. We need some memory for storing variables and the program itself. We need a serial port peripheral to talk to the host computer, your laptop. And we need a system bus to tie it all together. And don't worry, you don't have to do any of this. This is all taken care of by the Litex open source that we use. And you're going to be running software, TensorFlow. So already we have a complete system. You can run tinyML inferences with this, but you might not get the performance that you want. So that's where the fun part comes in. We're going to add some special sauce, this custom function unit that you add. And I'm going to go into more detail about what this interface is a little bit later. So here's some of the boards that we've tested. These are all known to work with CFU Playground. But these are boards that we haven't tested, but we test every night in GitHub Actions in the Renode simulator. So there's no reason that they shouldn't work. They have enough memory. They have a USB. So all of these should work, but we haven't tested them. So this is my first call for volunteers. It'd be great, especially if you have one of these boards, and there's a few dozen more, in fact. If you have one of them, to try to bring up CFU Playground and then write your notes up on the wiki page on our GitHub for supported boards. And if you run into issues, file an issue. What would you need? Well, you're going to need a Linux host. You would use Git. Basically, you just need to cut and paste the Git clone line. You will need to at least know how to modify some C++, but actually the code that we're modifying is closer to C. So if you know C, that's probably good enough. And a little bit of hardware design. If you know Verilog, that's great. But there's other languages that you can use. So these are some of the more modern languages. But the key thing is, as long as they can be translated or produce Verilog for the final combination with the rest of the system on the chip. And we use this nmegen, which is a Python library. And again, I'll talk a little bit more about that later. But you can actually have fun with this without even building a custom function unit. If you're interested in CPUs and performance, you can play around. Again, because we're building on an FPGA, the CPU itself is very configurable. You can change the branch prediction scheme. You can change the number of pipeline stages. You can change the cache sizes and see how that impacts your performance. And again, it's best to run on a real FPGA board, but you can actually get pretty far without an FPGA board by just running it in the simulation. Okay, why would you be interested in CFU Playground? Well, if you are designing a product on the edge and you want to include a little bit of tinyML, you could deploy with the system running on a tiny FPGA in your product. And this enables a really interesting, to me, was mind-blowing at first. Your firmware update doesn't just include a new ML model that maybe adds a new feature, but you'll have new optimized software to run that model that is tuned for a new CPU that it runs on. So you're actually updating the processor and all the software that runs on it with your firmware update. Or you could think of this as just prototyping for a RISC-V based ASIC that you're going to tape out. You think, well, yeah, that's just for big companies, but this is another project that's not part of CFU Playground, but I want to give a plug to, is go to efalbis.com, look for MPW, and there's actually this scheme where you, even an individual, can submit a chip design as long as it's open source, and they'll fab it for you and send it back to you in a few months. And Google will pick up the cost. So that's just a kind of an outside plug. This is a great way to learn a lot about ML hardware, software, how they interact, and how it affects performance. And we haven't really pushed on this last topic. It really unlocks new ML research opportunities, because you might have a new idea. It's a great idea for doing ML, but it just doesn't map very well to the existing hardware. It doesn't map well to GPUs. It doesn't map well to a CPU. But with CFU Playground, you have the opportunity to build the hardware that best supports your new ML idea. And this happens to tie in really well with this article that was just published in the communications of the ACM by another Googler, Sarah Hooker, who observed exactly this, that looking back, the ML approaches that have been successful are the ones that got lucky and mapped very well to existing hardware. So here you have the opportunity to come up with a new idea. And if it doesn't map well to the existing hardware, you can make your own hardware and in some sense, make your own luck. Okay, we're going to go a little more technical now, or actually this is probably a review for a lot of you. Some computer architecture. How does a RISC-V CPU work? And then we'll show how we extend it for the custom function unit. So let's look at an add instruction. This is the assembly if we disassembled the binary and we found an arbitrary add instruction. As the comment shows, we take register 4 and add it to register 7, add them together and put the result back into register 24. These registers are just, well, the RISC-V architecture has 32 32-bit registers, and they're used for temporary storage of variables. Now, when you're running on the CPU, the CPU doesn't understand this assembly instruction or the comment, it just understands the 32 bits of the encoded instruction. So let's look at that. The first thing the decoder does in the CPU is look at the rightmost 7 bits called the opcode. And here we see it has the ALU opcode. And that tells us it's going to use the ALU, the arithmetic logic unit that takes care of adds, subtracts, bitwise logical, shifts, stuff like that. And working on operands from the register file. And it also tells us how to interpret the rest of the 32 bits. So we look at the RS1 and RS2 fields. We look at them, see 4 and 7, if you can read binary. And that tells us that we want to pull out registers 4 and 7 and give them to the ALU. Then we grab these other 10 bits and give them to the ALU to tell it exactly what it's supposed to do with these 2 operands. And here we're telling it to do an add them together. And then the RD field tells us where to write the result back. So we're writing it back to register 24. So that's it. That's a complete add instruction. We get 2 operands, tells us what to do with them, add, and where to put the result back. The RISC-V instruction set has special opcodes reserved for these new custom instructions. So we have a new 7 bits up here. However, we actually, in our situation, we're going to interpret the rest of the bits in exactly the same way. We're going to get 2 source operands from the register file, send them, but in this case, instead of sending them to the ALU, we send them out to the custom function unit, which has your new operation that you've added to the instruction set. We're also going to send it the 10 bits. So the 10 bits that tells it exactly what to do. So in fact, you could define over 1,000 new instructions with this custom function unit. And we use the RD to tell it where to put the result back. So the pink line here is the interface between the CPU and the CFU. It is fixed. However, it is only logical. It's not a physical boundary. When we send it to the FPGA, that boundary just disappears. Everything gets optimized and placed and routed together. So in some sense, the custom function unit gets pulled into the processor and becomes an integral part of it. So actually, I've been a little misleading with this picture. It kind of implies that the custom function unit is always just a single cycle operation on 2 operands and immediately writes the result back, just based on those 2 operands. But let me be honest with you now. So yes, we can get 2 operands and 1 result for each instruction, but it can take multiple cycles. It can take variable number of cycles. So there's actually control signals that I haven't shown that indicate when the result is actually ready. And the CFU can actually refuse a new instruction, say, why don't you just hold on a bit? I'm still working on something else. There is no direct connection from the CFU to the memory, so it can't be twiddling with memory behind the CPU's back. The CFU cannot otherwise affect the CPU. It can't make it take a branch or anything like that. The CFU can contain state, which just means data that's stored in registers or in memory. and it persists from one instruction to the next. You can get as complex as you want. You can build your own sequencer. You could even build a tiny CPU in the CFU. We don't recommend that, but you could do that. And just by definition, a system has one CFU, but multiple instructions up to over 1,000 different instructions that can all access the same shared state in the custom function unit. So how do we use it? You might think, okay, well, the next step is you build a complex compiler that knows how to use these new instructions that we've added. Well, not in our case. In this case, you are the compiler. You're going to add the new instructions and you're going to use them. So it's up to you to insert uses of your new instructions into the code, specifically into the TensorFlow Lite Micro kernel code. After all, you're the one who just designed this new instruction to speed it up, so you know exactly where you intend to use it. This is how it looks from the software. I mean, this is how you access the new instruction from the software. It looks like a function call, but it's actually a macro that expands to just that single assembly instruction. So there's no overhead here. And we give it basically all the data that's would be in the assembly instruction. We give it the compile time constants that tell it exactly which custom function unit function we want. And then we give it the operands, but we just give it C variables, and the compiler takes care of figuring out what registers those variables are living in. And then you get a 32-bit result back that also is stored in just a C variable. So here's a concrete example, but it gets really hard to remember once you get a few different custom instructions, what is what. So we recommend that you always create a meaningful macro that instead of using the generic CFU op with the data, it just gives you a macro that with a meaningful name to directly perform that operation on the two operands. And here's a real example. So these new instructions just intermingle with your C++ code. So here's an example where we do a load through a pointer, do a couple of custom instructions, and then store the result back to the same location. And when we compile that and then disassemble it, we see that it has been compiled to exactly 4 assembly instructions. There's no overhead at all. Well, why do we like this approach for tinyML? Well, with ML kernels, the hotspots are small and they're very hot. You spend almost all your time in these inner loops of these ML kernels. And what that means is with a small amount of investment in custom hardware design that exploits the bit level configurability and parallelism of the FPGA, you can accelerate a very large fraction of the runtime. But because you don't want to try to build hardware that executes your entire program, because that would be enormously complex and not fit on the tiny FPGAs that we're targeting. We want to leave the complexity, like the initializations, the setup, and the outer loops in software where we know how to manage the complexity. And also, like as I mentioned before, the CFU can go from very simple to very complex. And we can take an iterative approach, starting very simple and then taking one step and then another step. Again, enabled by our rapid iteration until eventually we typically grow into an accelerator that is similar to what you see in research papers or from startups. Okay, one slide review of TensorFlow Lite for microcontrollers. The runtime interprets the ML model. It walks over the graph. When it gets to a node, it finds the right pointers. It takes the parameters from that node and invokes the kernel that performs the computation of that node type. So, and for example here, we see 3 convolution 2D nodes. They are all dispatched to the same code. But as I mentioned, we want to hyper specialize for the model that you have. So if as you're looking at your model, you see that they're all 1-by-1 convolutions, you say, okay, well, I'm going to special case when the filter shape is 1-by-1 in the spatial dimensions. And when I'm going to write a special convolution 2D just for that case, and when I see it, I'm going to dispatch to my specialized version. And if the parameters don't match that, then I just do the generic version. So this allows us to make a very specialized version that first we're going to specialize in software, and then we're going to accelerate by adding custom instructions. Okay, what is your experience using CFU Playground? Well, after you clone it, go through the setup process, and you're ready to start your first project, you will CD into your project directory, and this contains the custom function unit in Verilog or whatever your language of choice is. And it also contains your modified TensorFlow Lite kernels. So once we're in there, you just type make prog. And what this does is invoke whatever the right tools are for your board to build the bit stream, and then put that bit stream onto the board. So once you finish this, your board has your new modified customized processor. Then we built the software, compile the TensorFlow Lite for microcontrollers kernel and ours interactive software. And this is less than a minute, and then make load actually puts it on our customized processor and opens a channel so that you can communicate with it. And this is what it looks like. We have this interactive menu. So the top level menu, the first option is let's look at our models that we've compiled and linked in and loaded. So I hit 1 and you see, okay, here we've compiled 3 different models into our binary. There's person detection, micro speech, and keyword spotting. So I hit 3 to go to keyword spotting. You can run individual tests, or you can hit G to run all the golden tests and test the output to what they should be. So I do that. I see that they all pass, but maybe more interestingly, I always get profiling data to see how many cycles each layer took. And so this is unaccelerated. A convolution 2D layer is taking me about 11 million cycles. So these are in thousands of cycles. So the development starts, like you take a template project, copy it, that'll become your project. You choose the model you want to work on. You use this built-in profiling to figure out which op types are using the most execution time, because that's where you want to focus your effort. You look at the shapes parameterization, start doing your software specialization, and then you look for opportunities to add your custom instructions. And this is probably easiest to see in the example that I show later. You measure the result, and then you iterate. Okay, let's look at convolution 2D. So in the person detection, this is more than 3/4 of the execution time, so it makes sense to start looking here. So in a loop nest, it makes sense to go to the innermost loop and look at what we're doing there. Okay, well, we're doing basically a modified multiply accumulate. We take an input val, add an offset, do a multiplication, and add it into our running accumulation. So can we make a custom instruction from this? Well, remember that our custom instructions can have two operands. And this looks like it has 3 operands. So what are we going to do? And actually, if you really observe it, you see that it actually has 4 operands, because we take filter val, input val, and input offset, but we also add them to the old value of ACC, the accumulator. So there's actually 4 operands. So what are we going to do? Well, we make an observation that input offset doesn't change in the inner loop. So we use the fact that we can build the hardware however we want. We build a little storage location for input offset. We move it into the custom function unit before we start, and it just stays there. And what that means is every time we do, let me go back here. Every time we do this, we don't have to move in input offset because we've already stashed it in the custom function unit. And the same with the accumulator. if it lives in the custom function unit, then we don't have to keep moving it back and forth between the CPU and the custom function unit. And in fact, that saves energy by reducing the amount of data that we're moving back and forth. So it ends up looking like this. We have a storage location for the input offset, and we have the accumulator. And if you think about how this is going to work, we're going to need 3 or 4 custom instructions. We're going to need one to initialize the input offset register, move that in there. We're going to need an instruction to zero out the accumulator each time that we start doing a new accumulation. We need the main instruction that's executed the most for doing the multiply accumulate. And we might need another instruction to read the accumulator, our final accumulator, back to the CPU. And in case you're wondering what hardware looks like, I'm going to show you the Verilog. So it might look a little strange if it's the first time you've seen it, but hopefully it also looks a little bit familiar. In particular, if you look at this line, it is almost exactly how it looks in the C program. And down here we have if then else, which looking at the funct3 code, which tells us exactly which instruction we do, we see that it does different things depending on what those bits are. So we either load a value into input offset, we initialize the accumulator, or we update the accumulator. Okay, so going back to the TensorFlow Lite kernel, let's see how we use these instructions. So input offset is just loaded once, and we put it into the CFU. Then down here, this is zeroing out the accumulator, which we were originally doing in software, but now that the accumulator lives in the custom function unit, we need to zero it out over there. Here's the main instruction where now, because input offset and the accumulator live in the custom function unit, we only have to transfer the filter val and the input val over to the custom function unit. And finally, we get the result for subsequent use. So this is, and as I mentioned before, it is really useful to give them meaningful names. So here we define macros, CFU init offset, clear accumulator, multiply accumulate with offset, and get accumulator. So this is a pretty simple first example. And just this, we already have shaved a quarter of the execution time off our overall execution. So it's a pretty significant impact. But that is really just the start. We can go much further than that. And I'm going to kind of whiz through the rest of the evolution. Probably the first thing you notice is like, well, wait, these are 8-bit values, but all our data paths are 32 bits. Why aren't we moving 4 values around at a time? And yeah, that totally makes sense to grab 32 bits from memory, hand it over to the CFU, and let it unpack, sign extend, and do the operations in parallel, because this is the stuff FPGAs are really great at. Then we start storing some values that are reused in the custom function unit so that we don't need to keep shuffling them back and forth. And eventually we write a sequencer to do a complete multiply vector computation. We move the activation function and requantization into the custom function unit. And now we're operating on complete big chunks of data at a time. So we can be overlapping the computation of one chunk with moving the next chunk into the storage and pulling the previously computed chunk out. And that's actually much easier to see in this picture, where we kind of keep everything moving simultaneously thanks to a sequencer that we've built in the CFU. So that's quite a few steps from the starting point to where we ended up. But let's look at the performance impact. We started at 560 million cycles for doing this special version of convolution 2D with the 1x1 filter. And as we iterated, we see these speedups grow until we get a 55 times speedup for this operation. And so now we've reduced it from 560 million cycles down to 10 million cycles. So it is no longer a significant contributor, but as you can see, now we have another operation to worry about. But actually we stopped that because we started working with a different model. So that's as far as we got with MobileNet v2. But let me show you another example. Carl, were there any questions right now?
There are a few. There's a lot around the FPGA and FPGAs in general. Maybe we save those for the end. Let's see what else is. Unless you want to answer those now.
No, we can wait. I'm actually almost done. So
yeah, let's say let's just keep going, and then we'll just save them all for the end if that's okay with everybody.
Okay, thanks, Carl. So I almost didn't mention this example for sake of time, but I just have to talk about the intern project my super intern Joey Bushgar did this past summer. He really made CFU Playground tiny. So this is an FPGA board called Fomu. It is really smaller than a penny. It fits completely inside your USB slot. If you want to find out more, check out fomu.im. And yes, that's the complete URL. Even the URL is tiny. So he worked on keyword spotting, which, as you can see, it finished very quickly. It started very slowly. This is actually running. It's just running very slowly. If I hang out here long enough, you'll see the second dot appear. But in fact, it did not even start like that. It started by not running at all, because on that tiny FPGA board, there wasn't enough memory for the TFLM library and our software. So he actually had to do quite a bit of hacking just to get to the starting point. This is the custom function unit that this is actually a midway custom function unit. It's very small because we were very limited with the resources. And in fact, one of the key things he did was figure out how to steal resources back from the CPU to give them to the custom function unit. And so it's very much a system level optimization and trade-off. So a lot of it was actually not directly due to the custom function unit. He started out by optimizing the speed of the SPI flash that was being used. Then he played the games of, well, we don't have room for all of the program in the fast SRAM, so we'll move it to the slow flash, but we'll bring a few of the key parts of the software, the kernels and the ML model, back into the SRAM. So we had this very limited amount of fast memory, and he was very careful about what got to live in the fast memory versus what lived in the slow memory. You can see he played around with the iCache, other aspects of the CPU configuration, until finally he got a 75 times speed up, and he was actually very close to 100 times speed up on this particular model. Okay, I promised I'd talk a little more about how to generate hardware from Python. So yeah, the large CFU that Alan did was all designed in NMeGen, although it has recently been renamed to Aramanth HDL. So if you Google that, you can find more information. It's a Python library that you can use to generate hardware. So it doesn't magically translate arbitrary Python code into hardware. You still need to understand how hardware works, but it is much more convenient using Python rather than Verilog generate statements. So if you Google some of these keywords that I've highlighted here, you should be able to find Alan's presentation where he talks about that. So please join us in the fun. Here's our GitHub. Clone it. There's a lot of code there. We have documentation on Read the Docs. Please file issues, even file documentation issues, try out a new board, let us know how it goes. So raise a GitHub issue. You can email me directly at tcal@google. But even better than that is coming to our chat room, because if I don't happen to be there, then maybe someone else can help you. So that's it from me. So now would be a good time for questions.
Awesome, Tim. Thank you so much. That was really good. So let's see. There are a lot of questions. A lot around the FPGA board itself. But let's stick with the CFU one specific first. Let's see. Would CFU help in a memory bound up?
Memory bound. Yeah, okay. That's a great question. It can help indirectly with a little more work. For example, let's say you're memory bound by your ML weights. So you could try to come up with a compression scheme so that they are actually smaller in memory, which means that you actually have to move less data from memory, which will help you if you're memory bound. And while normally it might not make sense because you would spend too much time in software doing the uncompression once you get it into the CPU, by having a CFU, you can have this decompression occur in a streaming way that doesn't slow you down at all. So it kind of indirectly, you can help with memory bound applications. That's my quick off the top of the head answer.
Yeah, I think that's a good, like with work and focus. Yeah, you can do it. There's a few questions around power consumption. So is there power usage comparison done for TensorFlow Lite Micro on microcontrollers versus CFU? In general, like can we get estimates of power consumption on size of silicon to CFU? In general, what's the comparison between using CFU and like TensorFlow Lite Micro, just in terms of power consumption, if you know off the top of your head, or if you've done comparisons?
Unfortunately, I don't have hard numbers for you, but I will say I'm just as interested as you are, because as with all tinyML apps, power is one of the top, if not the top concern. So we are very concerned about power. And I mean, you can play some of the same games that happen inside microcontrollers. You can turn off the power to certain regions that you're not using. I guess kind of a very hand-wavy answer is if you can exploit the parallelism of the FPGA by doing a lot of stuff in parallel but slower, that's usually a win for energy. But on the other hand, of course, there is an FPGA tax of making things configurable. That just means you have more switches to go through. There is more capacitance on the connections. Let me just say, yeah, we're also very concerned and actually very interested in measuring power. I'll leave it at that, I guess.
Let's see. Still more on FPGAs. There's a question around the relationship between CFU and like TensorFlow Lite Micro. Does CFU will CFU be updated as TensorFlow Lite Micro software stack gets updated? How does CFU functionality? How is that different than ARM Ethos U55 other than open source? I think that's two questions. So how about focus on the how closely is the relationship between CFU and TensorFlow Lite Micro?
We actually have just recently made it so that we pull the current version of TF Lite Micro every night. So we are always on the head of master. Now, this does pose a potential risk. We're counting on the APIs not changing too much. And fortunately, TF Lite Micro is set up pretty well at the kernel boundary that the subroutine interface likely won't change, even if some internals change. But what this does mean is if you've invested some time in rewriting convolution 2D to use your custom instructions, and then there's upstream changes in TFLM that are incompatible, then it might break, and it'll be broken until you rewrite the new kernel to use your custom instructions. So that is a bit of a concern, but we haven't had any breaking changes so far in our use of TF Lite Micro.
Great. Let's see. There's a lot of interest from a workshop. Are you planning on doing a workshop on CFU anytime soon?
Yes, we are. However, it's just started, and it's great to hear that there's interest. We weren't entirely sure how it would be received, but actually send me an email if you want to be alpha tester, and as soon as we have early version of it ready, we'll let you go through it, and we'd be happy to send you some hardware if that helps sweeten the deal for you.
Great. Everyone, please send in more questions as you have them. Also, make sure you answer the poll for us. While we get let's say 1 or 2 more questions answered. Let's see. Do you have a recommendation for similar cost of Cortex-M MCU, low cost and low power FPGA to get started with? I guess for this, if someone wants to get started with CFU on an FPGA, I guess what's the cheapest power one in terms of cost and power? If you can think of one.
No,
because FPGAs generally be expensive.
Well, we've been talking about this daily with my new collaborators at Harvard about exactly what we want to use for this workshop that we're thinking about. And it seems like the ideal board doesn't exist, but maybe we just haven't found it. I like Icebreaker from 1-bit squared. It is still maybe $60. So yeah, I admit that's a bit more expensive than an Arduino board, but it is quite fully functional. Arty, even though it's large, it's a bit over $100, but it is really has all the resources you would want. It in some ways it's so big it's not so much tinyML anymore, since at least when I've been developing on it, I never was really too concerned about running out of resources the way that I was with Fomu. But yeah, we're still kind of searching for that ideal board. And there's a chance that we'll take a stab at designing our own board, but that might be a bit of a long shot.
No. I think that helps. I think most of the time when I think of FPGAs, I think of bigger and way more expensive things. So that Icebreaker seems like a pretty good place to start. That's not terrible. Let's see. There's a few questions around RISC-V and CFU. Are there any efforts to integrate the RISC-V vector extension in the baseline CPU? And then what sort of clock rates are you able to achieve for RISC-V and CFU? So performance questions around RISC-V and how does that integration work?
I've been talking to a faculty member at a university, and he was very interested in adding the RISC-V vector extension as a CFU, that is using the CFU interface. He had to bend things a little bit because there are certain aspects of vector instructions that kind of go around the limitations that I put on the CFU, specifically accessing the scalar register file. But it is certainly feasible. Actually, I think there was also a European project with Core 5 that also used their coprocessor interface to implement the vector instruction. So I guess the answer is, if VexRISC, the particular core that we use, does add support for the vector extension, then you can just add it and have both the vector extension and the CFU interface. As far as clock rates, it varies somewhat depending on the FPGA. We can easily hit 100 megahertz on the RD board. With Fomu, we usually run at 12 megahertz, but that is not so much that it can't run faster. It's kind of tied to the USB 48 megahertz frequency. For example, with Icebreaker, I think we run at 24 megahertz, so double that. And certainly running faster than 100 megahertz is possible. So this is where the kind of reality of hardware design comes in. If you throw too much stuff into your CFU in one combinational path, you will have difficulty meeting timing. And then you're doing this back and forth of balancing the hardware that you build, inserting registers to break it into cycles to keep your clock rate high. So yeah, that's where definitely you will have to, recognize that you're building hardware.
Cool, thank you. Let's take one more question, and I'm going to go with what kind of at-a-glance benchmarking results does CFU offer, say, to compare performance with custom function units versus without?
Well, running on the board, you can always compare against a non-accelerated version, kind of an apples to apples comparison, CFU without CFU. And we use a completely accurate cycle counter and we also have additional counters that you can control and pause and restart for counting cycles. That's actually one of the main benefits of actually running on the board. You know that you're considering all the delays from memory contention because you're actually counting the real number of cycles that you're running. We do want to work more with, especially with the Harvard group, since they're running the MLPerf tiny benchmarking competition. And we would like to kind of, even if it's an apples to oranges comparison, actually do some comparison against actual microcontrollers and even specialized accelerator ASICs, whatever. And so we can do this comparison across all these different approaches. And I'm sure some of them will definitely beat us in pure performance, but there's these many other aspects why for us, the building on an FPGA is a good alternative.
Yeah, that's awesome. Yeah, I would expect an ASIC that with its specific function, optimization could be better in that specific case, but there's a lot of flexibility to FPGAs.
Exactly. We are not going to beat an ASIC doing what that ASIC was designed for. But
right.
FPGAs have the flexibility and the openness that are really important to us.
Well, that's great. I think we're at time. So send any other questions to Tim or reach out on the GitHub page is probably going to be your best bet. Again, Tim, thank you so much. Let's see. Let's just do quick closing.
We would like to thank our tinyML Talk strategic partners, and then we'll go with each of the slides for the company. So we have the executive strategic partner. We would like to thank ARM, the software and hardware foundation for tinyML, Edge Impulse, the leading edge ML platform, Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, that have neural decision processors, ML training pipeline, data platform. Also, we would like to thank our platinum strategic partners. That would be Deployed. We use AI to make other AI faster, smaller, and more power efficient. Quick Attack, global IoT solutions. Reality AI, that add advanced sensing to your product with Edge AI and tinyML. Renaissance, broad and scalable edge computing portfolio. Also, we would like to thank our gold strategic partners that are Maxim Integrated, that is part of Analog Devices right now. So it's enabling edge intelligence latent AI, adaptive AI for the intelligent edge, micro AI, NXP, Seed Studio, the IoT hardware enabler, tinyML, that builds smart IoT sensor devices from data, ST, Sense builds sensing and interference hardware for ultra-low power embedded mobile and edge devices. Also, we would like to thank our silver strategic partners that are AON Devices, AMZ Visual Sense, Greenwaves Technologies, Groverting Corporation, HOTG, ImagineMob, Kitso, Prophecy, Rixon, SAP, and Stream Analyze. Thank you very much. So please join us on Tuesday at 8 a.m. as usually. And also we'll be having one more talk on Thursday that will be Toronto talk. Will be starting at 8 a.m. Thank you very much. We would like to thank again for everybody's attention. Thank you very much, team, for joining today's call, for being our presenter, and for your interesting and interactive presentation today. Thank you very much.
All right. Thank you for having me.